What's up, guys? Sim Science back at it again. If you watch my first intermolecular forces video, you will hear that my mic was muffled. All right, we're figuring it out together. So it's late. I'm tired, but we got to bang out another one because I can't do that to you guys. All right, so let's do this. Intermolecular forces. Intermolecular forces. Okay, inter. That's what we're talking about here. Inter is between. Intra is within. Okay? You interact with others. You talk to somebody else. You're interacting. But when you're talking about intra, you can be introspective. I know it's intro with an O, but it's the same idea. Introspective. And you're looking within yourself to figure out what you can change so that you can interact with more people and maybe get some friends. And sometimes you spend a lot of time introspecting because you don't have anyone to hang out with and you still can't find friends. But that's okay. That's not what we're talking about right now. We're talking about other things. So intermolecular forces, that's when you have one molecule, molecule 1, and molecule 2. And within them, they have all these intramolecular interactions between atoms, and they have their own intramolecular interactions. And then they find a reason to interact between each other, and that's where it becomes intermolecular. Okay, intermolecular forces. First one we're going to talk about, London dispersion forces. Okay, so what's going on here? Well, every atom has a nucleus, a cute little nucleus, and around every nucleus, I gotta do that, okay. Around every nucleus is an electron cloud. Okay, an electron cloud, we learned in atomic theory that these electron clouds we're uncertain about them. We know they exist and we can guess where the electrons are, but we don't really know. So they have electron clouds. Now, what's going to happen if one of these molecules goes at the other one hard? Okay, so let's say this guy over here on the right goes at this guy hard. Well, the electron clouds have a negative charge, right? Because they're made up of electrons, and the nuclei have positive charge because they're made up of protons and neutrons, and protons are positive. So these electron clouds, when they get close to each other, they're going to repel each other. But one of them is going to win. One of them is going to be stronger. And let's say it's this guy. Okay, so let's see what happens there. So we have our nucleus again. And now that they've gotten close together, these electron clouds, we're going to have something a little bit different. This electron cloud is going to be scared. It's going to be pushed back away from the oncoming electron cloud of the first, or of the stronger of these two atoms. I guess that works. It's kind of thick, but that's okay. All right, so this electron cloud in the first one here, so this is what happens after this interaction. This electron cloud got pushed back, and now this positive nucleus is exposed to this negative electron cloud. And this negative electron cloud is running away from the other electron cloud, and this positive nucleus is left out in the dust. So this interaction is now occurring between the positive nucleus that's exposed and the negative electron cloud that's come closer. So we have a positive and a negative side. We've formed a dipole. Dipole, two poles, opposite charges, opposite whatever. Magnets have poles because they have positive and negative sides, and these atoms now have poles because they've exposed a positive on one side and a negative on the other. So they've formed a dipole, specifically a temporary dipole. Because as you can imagine from the way I just described this happens kind of randomly when atoms get close to each other and the electron clouds interact and then expose the other charges. This is what happens. So this is kind of a shifty intermolecular force. It's kind of random and it's temporary. So this is actually the weakest of the intermolecular forces. So the weakest force. All right, but basically what's happened is you're having two atoms interact. And the thing about this force, London dispersion forces, some just call them dispersion forces. London was some guy or something. London dispersion forces, the thing about them is they exist all the time between everything, because this can happen to any atoms interacting. And oftentimes it happens to the same atoms when they're near each other. So it's not a bond, but it's an attractive force that exists. And a lot of times, and on our PowerPoint, you'll see it drawn as two oval kind of shaped things where the charges are being pulled apart. And this is why what I drew with these electron clouds, it turns into two ovals, and the opposite charges attract to each other. So that's what a London dispersion force is. You can think of it as the electron cloud being dispersed away from where it was before because another electron cloud's coming in. So like everything else we'll see with these forces, it has to do with the charges and the charges interacting. Okay, so let's move on to the second thing we're going to talk about, which is dipole-dipole interactions. Dipole-dipole. What do you like to call it? Dipole-dipole, which is pretty funny. So we can roll with that. Just kidding. I'm not going to lie to you guys. So dipole-dipole. Let's stick with the same color theme from above. So let's say we have an atom that has a big negative portion and then a smaller, oh, that's too big, a smaller positive little kind of nub on top. We'll draw a few of these. This is, you probably don't like watching me draw. It's kind of just part of the game. Do one more. All right. Okay. So the blue like up here is positive, and I can label that real quick for you. So all of these blue are positive, all of the green are negative. So what's going to happen here? Well, they're going to interact. You're going to have your positive attracted to your negative, positive attracted to negative, positive attracted to negative, and maybe sometimes they can even be attracted to more than one at once, and it's going to orient all these things. So again, dipole-dipole, we're working with dipoles. We have a positive pole here and a negative pole here. These are polar molecules that exist around each other with the opposite charges on them, and they attract each other through those electrostatic forces of positive and negative. It's all about the charges attracting each other to each other, or attracting each other. Okay? So they align their oppositely charged regions, and that's how they exist. I could draw 100 other ones of these and draw all these little orange connections between them, and you'd see a ton of them interacting. So that's basically dipole-dipole, two different poles interacting. So there's not really much more I can say about that. Now, the last one we're going to talk about is hydrogen bonding. Hydrogen bonding. So hydrogen bonding is really just the strongest of the dipole-dipole interactions. So strongest dipole-dipole. There's nothing really that special about hydrogen bonding other than it involves hydrogen. So it's always going to involve hydrogen bonding to three specific elements. And see real quick if you can think of those. Hopefully you thought of oxygen as it interacts in water, bonding to oxygen. Nitrogen is another one, or fluorine. Okay, so these three specifically. It's basically a dipole-dipole interaction between a positive hydrogen and a negative oxygen, nitrogen, or fluorine. And if you look at the periodic table, you'll see that these three elements are three of the most electronegative elements out there. They're going to draw electrons to themselves with the most power, and therefore they're going to become negatively charged more easily. And then the hydrogens, which give away their electrons easily, are going to quickly gain a positive charge and be attracted to them. So Hydrogen bonding is basically just dipole-dipole interactions, but with the positive being hydrogen and the negative being oxygen, nitrogen, or fluorine. And most of the time we use water as this example. So for water, let's draw a few. I'll do oxygen in red. It's almost always represented in red. So understand that oxygen is red in this case. And then for the hydrogens, we can just stick with blue for this video. Blue, blue. We can draw some more. Okay, back to red. Okay, so these all have their connections now. A bunch of water molecules. Okay, so all these little blue dots are hydrogens. I'm not going to label them all, but they're pretty much them all. I guess I might as well go all the way. Hydrogens, and then we have oxygens here. So as we talked about before in class, the oxygen being more electronegative is going to draw these shared electrons closer to itself. And then on top of that, it has its lone pair of electrons up here. So it's more negative. More negative. All the oxygens are more negative, and all the area with the hydrogens is more positive, because hydrogen is just one proton and one electron. And since its electron is getting drawn closer to oxygen, it basically just becomes a proton on a stick. Proton on a stick, and a proton has a positive charge, so it's just a positive charge on a stick. Now, within the molecule itself, you have the covalent bond between oxygen and hydrogen, the covalent bond. And sometimes you'll hear that referred to as a intramolecular hydrogen bond, so a hydrogen bond to oxygen or nitrogen or fluorine within a molecule. Just so you know, you don't really need to concern yourself with that too much, because when we talk about hydrogen bonding, we're talking about the intermolecular reaction or attraction. So let's say this hydrogen being attracted to this oxygen, because this is positive and that oxygen is negative. And then this hydrogen being attracted to this oxygen, and this oxygen being attracted to this hydrogen, and this oxygen being attracted to this hydrogen, and this being attracted to this, and so on and so on and so on. You could, like the other dipole, you could draw a million of these and show all the interactions. But the only real difference here is that you're talking about hydrogen bonding to oxygen, nitrogen, or fluorine. That's what makes a hydrogen bond a hydrogen bond. And because hydrogen is has such low electronegativity, and oxygen has such high electronegativity, or oxygen, nitrogen, and fluorine, this is the strongest intermolecular force. Okay, this is the strongest, and then a typical dipole is a moderate force. It's stronger than London dispersion forces. I was doing the forces, and I thought I was doing them in orange. I was doing them in purple. That's okay. We'll just underline this in orange. It's all fine. London dispersion is the weakest. Hydrogen is the strongest, because hydrogen is basically a stronger dipole between these specific atoms, and then dipole is moderate. So the way we talked about this in class, and one of the important ways to think of it is how difficult it is to break these bonds. And I'm putting bonds in air quote, because with all of these, including hydrogen bonding, it's not really a bond like ionic or covalent. There's no sharing of electrons. It's just an attraction. It's a force that exists between a positive and a negative. So the way to measure these is how difficult it is to break up that force of attraction. And we can think of that when we think of evaporation or boiling. When you do that, when you turn these things into a gas, you're doing that by breaking the attraction. You're releasing water molecules, for example, with hydrogen bonding. You're releasing water molecules as gas, as water vapor. So because they're the weakest, London dispersion forces are the easiest to break. Dipole, again, are medium, so it takes longer to break them than London dispersion, but not as long as it takes to break hydrogen bonding. So longest to break or longest to evaporate, that's what we're talking about when we bring in evaporation. So hydrogen bonding are the strongest of these. As we learned in class, this is what holds together our DNA. This is crucial to protein structure and all those things. So these are the three different intermolecular forces that with molecules interacting between interacting with other molecules, so interactions between separate molecules. You have London dispersion forces that, like I said, are a little shifty, kind of weird, only happen temporarily, and are a little bit unpredictable. They're the weakest, but they exist all the time between every atom. So they're the most common, they're always there, but they're the weakest. Dipole-dipole exists between molecules that have poles, that have a positive and negative end, that attract other positive and negatives, or negatives and positives respectively. So the positive always attracting a negative and the negative attracting a positive. And then hydrogen bonding is a dipole-dipole on steroids, basically, because you have the hydrogen and then you have these three atoms that create really strong dipole-dipole that separate themselves from a typical dipole-dipole. So that's all for this. Hopefully you heard me a lot better in this one. And yeah. Comment, like, subscribe. Any questions you have, comment below, and I can hopefully answer them either in the comments or with another video. Thanks, guys.